Hello everyone, hope you're all doing well. So in our last video we have seen the notion of limit. So our today's topic is limit of a function, limit of a function at a given point. Okay, so today's topic is limit of a function at a given point. So before getting into today's topic, I request you to have a glance on the following topics. The first one is what is called function. As it is very clear, very obvious, we have known it that function is like a machine. If we give any input, that will give us a unique output. Yeah. So basically, to define a function, we need three things. One is the domain, and another one is called the codomain, and the third one says the rule. That is, the which element of domain should be mapped with the which element of codomain, right? Okay. The second thing is how to represent a function graphically. That is, how to represent the given function in a Cartesian plane. Take your domain in x-axis and take the codomain in y-axis, right? And denote the corresponding order pairs and then connect them by a line, or else more detail about it we will learn in curve sketching topic, right? Okay. The second thing is how to represent a given function graphically, and the third one is the notion of limit. That is our last video. So before you start to watch this video, please have a glance about in detail about these three topics: what is function and graphical representation of function and the notion of limit. So to start today's topic, let me start with one function. Say my f is a function which defines from real numbers to another set real numbers. Okay, so this is domain, codomain. Say let me take my rule f of x is equal to, simply let me take x plus 1, a linear function, right? Okay, so is it a function? Yes, it is your duty to check because we have learnt it already, right? Yeah. Okay, so you just check and convince yourself that it is a function. If you have any doubt, just contact me. Okay, so the graphical representation of a function, let me make it a bigger diagram. Okay, yeah, this is my domain and this is my codomain. Say f of x plus 1, say this is 0, and say this is 1, and this is 2 and 3, so 1, this is minus 1. Say like this, it is 1, 2, 3, 4 and so on. Okay, the negative numbers are there. So if I give 0 as an input, my f of 0 will be 0 plus 1, 1. So for 0 I will be having 1. For 1, f of 1 I will be getting, f of 1 is equal to 1 plus 1, that is 2. So here for f of is equal to 2, I will be getting 3 and so on. So since it is a linear function, it will be like a straight line. Okay, just consider this as a straight line, okay, for a moment. Okay, fine. So we have made a graph of the given function, right? So now, in last video we have seen what is called the limit of a particular expression. Now I'll write the notation, say x approaches 2. What is the meaning of that? It means my variable, the x, takes the value nearer to 2. Am I right? But not equal to 2. Fine. Look at this graph. Here it is 2 and x is my domain value. My x approaches 2 means in which way I can approach the number 2? Listen it. 1, 1.1, 1.5, 1.8, 1.9, 1.9999, 1.99999. So in this way I can approach the number 2 by walking on this line, right? Or else there is another way to approach the number 2. How? Yes, here is 3, 2.5, 2.4, 2.1, 2.001, 2.001, 2.001. So from the right I can walk and approach the number 2. Is there any other way to approach 2 on this real line? No, right? So if the number is here 2, I can approach the 2 from the left of 2, or if the 2 is here, I can approach this 2 from the right of 2, right? So there are two ways to approach this 2 by x. Am I right? So the one way is approaching the 2 from the left of 2, that I represent by this notation, that is 2 minus. Look at this, x approaches 2 minus. What is the meaning of this notation? X values are approaching the number 2 from the left of 2. Fine? Okay. The another notation, x approaches 2 plus. What is the meaning of this notation? My x variable value approaches the number 2 from the right of 2, like 2.5, 2.4, 2.1, 2.01, 2.001, 2.001 and so on, right? So just understand the notation. X tends to 2 minus means x approaching the number 2 from its left. X tends to 2 plus means x approaching the number 2 from its right. Is it fine? Okay. So now look at this. If my x value is 1, my f of x value is 1 plus 1, 2. If my x value is 1.5, then my f of x value is 1.5 plus 1 is 2.5. Am I right? Here is 2.5. If my x value is 1.9, my y value, f of x value is nothing but 2.99. Am I right? If my x value is 1.9999, then my y value is plus 1, that is 2.999. Am I right? So look at this carefully. For this point, this is functional value. 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 Zoom it and look at it. As my x approaches 2 from the left, as my x approaches nearer and nearer to 2, my f of x value approaches nearer and nearer this point. That is in codomain, which value it approaches? 3. So for x is equal to 1 means f of x1 is here. For x is equal to 1.5 means f of x is here. For x is equal to 1.9999 means my f of x is 2.99999. Am I right? So what we are seeing from this diagram, as my x approaches the number 2 from the left, my f of x value approaching the number 3 in codomain. Isn't it? Do you observe this? Can you feel this? Right? Yeah. This is what we are going to write now. So what we are seeing, what we are observing from this function means, as my x value approaching the 2 from the left, my f of x values are approaching the number 3. So how to write it mathematically? This is how we write it. That is, the limit of the function f of x as x approaches 2 minus. So what is the notation of this? What is the meaning of this notation? The limit of the function f of x as x approaches 2 minus, which means as x approaching the 2 from the left. What we are seeing, our f of x is approaching the number 3. Yes. Fine. So limit of the function f of x as x goes to 2 minus, we are getting the number 3. So this is what we say, the left hand limit of the function f of x at x is equal to 2. So as my x approaches the number 2 in domain from the left, my f of x value approaching the number 3. Yes. So this is simply, we will say LHL. LH means left hand limit. Fine. Yeah. So yes, of course there is another way. What is that way? We can approach the number 2 from its right. Say 3, 2.5, 2.4, 2.1, 2.01, 2.001, 2.001 and so on. Right. For this 3, our output is 3 plus 1 is 4. For 2.5, it is nothing but 3.5. For 2.1, it is 3.1. For 2.01, we will get 3.01. For 2.001, we will be getting 3.001. So for 2.0001, we will get 3.0001. So look at this graph. As we approach the number 2 from the right, our f of x values are also approaching the number 3. Do you see that? For 3, it is 4. For 2.5, 3.5. 2.1, 3.1. 2.01, 3.01. Right? So as it comes nearer and nearer here, our f of x values are coming nearer and nearer 3. Yeah. So how we can write this? So the limit of the function f of x as my x approach 2 plus. What is the 2 plus? Yes, we are approaching the 2 from the right. Yes. What is the value we are getting here? This is also 3. So this is, we say, this is called right hand limit of a function at x is equal to 2. Do you get me? So let me brief this again. Limit of f of x as x approaches the 2 from the left, our f of x approaching number 3. So limit of my x as my x approaches 2 plus, my f of x approaches the number 3. So this is called right hand limit because we are approaching, in this case we are approaching the 2 from the right. Is that okay? We say the left hand limit exists for the given function at a given point if we get this number as a finite number, because in some cases we may get plus infinity or minus infinity. In those cases we don't consider that as a existence of limit. Okay, so when you find this limit of a function at a point, whether either approaching from the left or from the right, you should get a finite number, then only we can consider that as a limit. Okay. So in this example, what we are observing is for the given function f of x is equal to x plus 1 at the given point x is equal to 2. See, make sure that we are analyzing the existence of the limit for the given function at the point 2. We are taking one point in domain and at that point we are checking whether for the given function whether the limit exists at x is equal to 2 or not. So how we are seeing, in how many ways we can approach the 2, that is we are seeing. We are seeing that we can approach the 2 in 2 ways, that is one from the left, another one is from the right. So we are seeing that as we approach that number 2 from the left, our f of x values are approaching the number 3. Yes. And another thing we are seeing that as we approach the number 2 from the right, our f of x value is also approaching the number 3. So our left hand limit for the given function at x is equal to 2 is 3. Our right hand limit for the given function at x is equal to 2 is also 3. So in this case, what's happening here? Our left hand limit is equal to right hand limit. So we can say the limit for the given function at the given point x is equal to 2, the limit exists. So simply we can say the limit of the function f of x as x approaches 2, we write simply 2, is nothing but 3. So this is what our final statement. For a given function at a given point 2, the limit exists. Why? Because we are analyzing two things. We are finding the left hand limit of the function at x is equal to 2 and the right hand limit of the function at x is equal to 2, and if they equal, then we say the limit exists. So now let me give you a formal definition. For a given function f of x and at given point x is equal to a, we can check whether the limit exists or not by following these rules. First rule, find the left hand limit for the given function at a given point. Second one, find the right hand limit for the given function at a given point. If both exist as a finite number and both the numbers should be equal, then we can say for the given function at a given point the limit exists. What is the limit value? There is nothing. In both the cases you are getting the same finite number. That number plays as a limit of the function at x is equal to a. So how we write all these things in a single line? This is what limit of the function f of x at x is equal to a is, say if it exists some k, then we will write it as a k. Is that fine? Find LHL, find RHL, and if they are equal, then we can say the limit exists. The limit value is nothing but what the value you are getting in LHL and RHL. Fine. But is this enough to understand this topic? No. See, in mathematics, we always do a particular form a particular method. We will read the definition, we will see some examples which supports that definition, and we will go for the problems and we will move to the next topic. But this is not the right way of learning mathematics. This won't give you to understand the core content. So what way we have to follow? It is not just reading the definition and supporting example. Whatever definition you read, you find the negation of the statement and go through some examples which supports the negation of the statement. What is called negation? The case where it fails, the definition fails. For example, now we have seen the limit of the function at x is equal to a. That is, when for a given function at a given point the limit will exist. But what we have to learn extra with this, when for a given function at a given point the limit does not exist, that is what the negation of the statement. And we have to see the examples where this negation occupies, right? So we will see such examples now. That will lead us for a very good understanding actually. Look at this. See, let me modify the given function simply. For example, say my f is from R to R and my f of x is, say, the same x plus 1, but this is x plus 1 if x is less than or equal to 2, and say x plus 2 if x is greater than 2, right? So, okay, this is LHL, this is RHL. Okay, now I have modified this function. How I have modified? 5, 6. If my x is 2 or less than 2, my functional value is x plus 1. Yes, when x is 2 or less than 2, the graph is as it is, x plus 1. If x is greater than 2 means my functional value is x plus 2. Say for example 3 is greater than 2. So my functional value is 5. So for 3 I will be getting 5. So 2.5 I will be getting 4.5. Am I right? So 2.1 I will be getting 4.1. 2.001 I will be getting 4.001. Am I right? For 4 I will be getting 4 plus 2, 6. So look at this graph, it goes like this. Am I right? But for x is equal to 2, what is the functional value? X is equal to 2 is here, so 2 plus 1 is 3. For x is equal to 2, that is 3 only. Here we write a whole, because when it's strictly greater than, for 2 the image is here. For greater than 2, it starts from here. Am I right? So okay. Now look at this graph. Same thing we shall do. We shall approach the 2 from the left, then we shall see what is the limit. Yes, look at this 2 is here, we shall approach the 2 here, but where the function value approaches this point, that is nothing but 3. So the left hand limit of the function at x is equal to 2 is nothing but 3, because for this it is output, for this it is output, for this it is output. So for 2 also this is. So as we approach the the number 2 from the left, our f of x is approaching the number 3. So for this the LHL is the same 3. Look at the right hand limit of this function at x is equal to 2. When we approach the number 2 from the right, for 3 it is here, for this point it is here, for this point it is. As you come nearer and nearer to from the right, where your f of x values come nearer and nearer, that is 4. Do you see that? For this point it is here, for this point it is here, for this point it is here, for this point it is here. So as we approach the number 2 from the right, our f of x values are approaching the number 4. Am I right? That is 4. Okay. So the right hand limit of this function, when we approach our x, when we approach the number 2 from the right, our limit value is nothing but 4. Is it clear? Yes. So we are checking the limit of the function at x is equal to 2. To check the limit of the function at a point, what we have to do? We have to find the LHL and RHL. Here in this case, our LHL we are getting 3 and our RHL we are getting 4. Both the values exist. Yes, of course they are finite, but they are not equal. Am I right? LHL is not equal to RHL. So in that case, we can say only this much, that is the limit of the function at x is equal to 2 is, as x approaches 2, does not exist. Fine. Why it does not exist? Because at the given point we are seeing the left hand limit, we are getting that is 3, and at the given point we are seeing the right hand limit, that we are getting 4. Yes, both the limit exists, but the left hand limit is not equal to right hand limit. So we can say the limit does not exist for the given function at x is equal to 2. We have analyzed only at 2, and that 2 LHL is not equal to RHL. So we can conclude only this much: the limit does not exist at x is equal to 2 only. In other points, whether the limit exists or not, that we don't know. We have to go take that one, and we have to find the LHL at that point, RHL at that point, and then we have to compare it, and then only we can come to the conclusion, right? So this is an example where the limit does not exist, but the left hand limit exists and right hand limit exists, but they are not equal, so the limit does not exist. So is my next question: for any given function at any given point, will always left hand limit and right hand limit exist? Let us see this example. Say, let me do a small modification. Say for example, if x is, let me take a simple example. Say x is equal to 2, if x is less than or equal to 0, and say if x is greater than 0, my function value is 1 by x. So look at the graph of this function. So this is on, and this is also on. If my domain value x is 0 or less than 0, my function is nothing but a constant function, that is 2. For all these numbers, my graph is nothing but 2. Sorry, let us take it as a horizontal line, okay, which passes through this number 2. When x is less than or equal to 0, it is nothing but a constant function 2. If x is greater than 0, it is nothing but 1 by x curve. You know how to draw the 1 by x: 1 by 1, 1 by 2, 1 by 3, and when you take the reciprocal, the values will increase, am I right? So the 1 by x graph will be looking like somewhat like this, am I right? Yes. Okay. If you don't know how to sketch it, please ask me. Okay. So now look at in this case. Now let us check limit of this function at x is equal to 0. So to check the limit of the function at x is equal to 0, what are the things we have to go through? We have to find the left hand limit at x is equal to 0, we have to find the right hand limit at x is equal to 0, and we have to check whether they exist and find it and they are equal or not. Let us see that. Let us check what is the left hand limit at 0 and what is the right hand limit at 0. Let us see. Okay, we don't know what is that. See, 0 is here, am I right? You approach the 0 from the left. For this it is output, for this it is output, for this it is output. So as I approach the number 0, my left hand limit, my functional values are approaching the number 2. It is constant 2 for all the outputs. For minus 1 also it is 2, minus 0.5 is also 2, minus 0.1 is also 2, minus 0.00, minus 0.0001 is also 2. So for all the values it is just a constant value. It is the output remains as 2. So my left hand limit is nothing but 2 at x is equal to 0. But look at the right hand limit at x is equal to 0. 0 is here. You approach the 0 from the right. For this point, this is the output. 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 See, look at here. As you approach the 0 from the right, as you come nearer and nearer 0 from the right, your outputs are, your functional values are going as higher as, you know. So, if you take 1 by 100, your output is 1 by of 1 by 100, that is nothing but 100, right? If you take 1 by 1000, that is 1 by of 1 by 1000, that is 1000. If you take 1 by 1 crore, your output will be 1 crore. So as you come nearer and nearer to 0 from the right, your functional value is going higher and higher towards where it goes towards. Yes, it goes towards infinity. It goes without any boundary, right? Because as much as you come nearer to 0 from the right, your outputs are going higher and higher and higher. So what's happening here? The limit of the function at x tends to 0 plus. When you approach the 0 from the right for this 1 by x function, your functional value moves towards infinity. Am I right? Yes. So in this case, look at this. Here, limit of the given function, to check the limit of the given function, we are checking LHL and RHL. The limit of the function as my x approaching 0 from the left, it is nothing but 2. But the limit of this function as my x approaches the 0 from the right, it is infinity. So this is how we climb the result. Here the left hand limit exists because we are getting a finite number, but we say right hand limit does not exist. Why? Because we are getting as an infinity. Infinity is not a number. We can't do anything with that symbol infinity. Am I right? So here LHL exists, but RHL does not exist, because if we are saying the limit exists, means that should be a finite real number. That should be one of the real number. Then only we can say it exists. Since it is an infinity, we say that RHL does not exist. So whether the limit exists at 0 or not? Yes, of course it is not. Because when we can say the limit exists at a given point, if the LHL exists and RHL exists, and if they are equal, only then we can say the limit exists. And what is the common number? That is what the limit value. But here LHL exists, but RHL does not exist. When it doesn't exist, how can we say, analyze whether that is equal or not? So we say in this case also the limit does not exist. So we can compare itself here. Am I right? So here is also, as the limit of this function as x approaches 0 does not exist, because for the existence of this, LHL should exist, RHL should exist, and they both should be equal. So let me brief our today's topic with just 2 lines, right? So for a given function at a given point A, we say for this function at the domain at this point, the limit exists when we find 2 things. One is LHL and RHL. What is LHL? That is limit of f of x as x goes to a minus. What is RHL? The limit of f of x as x goes to a plus. Okay. This should exist as a finite number. This should also exist as a finite number, right? If it is a finite number, then we say LHL exists. If this is also a finite number, then we say RHL exists. And if both of these numbers are equal, then we can say this limit exists. Am I right? So find LHL, that should be a finite number, RHL, that should be a finite number, and they both must be equal. Then we can say limit of the function f of x at x tends to a exists, right? And that common value is going to be the limit value. But if both of these exist but they are not equal, then what can we say? Yes, the limit of the function at x tends to a does not exist, right? And another possibility is it may not be a finite number. If any one of them is infinite, in that case also we will say the limit does not exist. See, these examples alone are not enough. We have to see many and many examples, different examples. But most of the examples will fall one of these 3 categories. So it is, if you understood these 3 kinds, it is very easy to read and understand the remaining examples. It is very important not just for a limit alone. We have seen the notion of limit. With that idea, we have built the concept of limit of a function at a point. This as a base, then we will define the definition of continuity of a function at a point and for the whole domain. With that as a base, we will go for differentiability. With that as a base, we will go for application of derivatives and integrals and so on. So these are the very crucial parts in calculus. So if you have any doubts, just contact us. Thank you.